Dakle, sljedeće predavanje kolega Davor iz Infobita govorit će nam malo o real-time big data, kako su to kod sebe implementirali, kakva iskustva imaju, pa kolega Davor.
Hvala. Dobar dan, ja ću se isto prebaciti na engleski i nadam se da neće biti problem i da neće to tako loše zvučati. Hello, welcome to Javantura. My name is Davor Poldrugo and I'm a software engineer at Infobip. Today I'll be talking about real-time big data ingestion and querying of that aggregated data. My name is, I said also, before it's Davor Poldrugo, and I like software engineering and backend development, highly available systems. More of this you can check on the link. First of all, think about Infobip, the company where I'm working. We're a mobile messaging platform, a member of various professional associations, and we're doing several things like professional SMS, number validation, voice, and USSD mobile payments. But of course, it's of course SMS business. We provide various enterprise products, and we also have clients like big companies and small app developers. Something about the numbers. That's our global numbers about how much countries we have covered and operator agreements. But here are no numbers about our development offices. We have like for development offices 150 developers plus. Mostly in Croatia, Bosnia, and Serbia, but we're also extending to Russia something, and we're also hiring, so check out with us later. First of all, I will just put the things in this presentation which will be in this order. First of all, I will talk about the dictionary, the words I'll be using. Of course, big data buzzword, how will I use it, because everybody has its own definition of big data. Our real-time use case, and then because a real-time use case, you don't have it if you have small amounts of data. So you just, I will talk how the our platform evolved and got to this position where we needed to approach these things differently. And of course, this is our path towards real-time data. And of course, the architecture we tried to use and used to achieve this real-time thing. And at the end, I will talk about some numbers that we achieved and some kind of conclusion how we reached this real-time. Okay, first of all. I think everybody knows what is real time, but just to be clear, in this context, it will be used like when data enters our systems, and the time when it is ready to be queried by another of our systems. Or end user can see it. So that's the meaning of real time here. We want to, as soon as the data comes in, we want to be able to query it on another part of the system. And of course, the buzzword, big data, we're not a company like Facebook, and we're not having those kind of data. But this definition of accumulation of data that is too large and complex for processing by traditional database management tools is strictly, it will be used as this. We don't have, as I said before, that kind of amounts, but we will use some of those approaches used by those companies to achieve this use case of real time. And another key word is ingest or ingestion. I will use it as in a figurative meaning at the bottom, ingesting a large amounts of information very quickly. And this term will be used when our systems will be reading data or pushing or pulling or something like that, but in the ingestion will be the word. Okay. I guess I don't have the top of my slide is missing on the But it says the real-time use case and the challenges. Here's only challenges. Okay. So our use case, we have a web application that uses that sends some kind of campaign of SMS messages. It can be big amounts, like millions of 100,000s, and we try to track it in real time. But our current system, when we send a campaign and the campaign starts progressing, as it progresses, the amounts of total traffic, of course, and the expenses are becoming bigger. But at the end of our campaign, when our system has all those messages have arrived and been sent from to our system, this status of progress becomes finished. But those numbers of total traffic and expenses are still climbing. And they can climb like for several minutes or for sometimes seconds, but sometimes even more than 30 minutes. So we had to try to solve this problem. And this is our use case I'll be talking about. So, but to reach, yeah, of course, there's another thing missing here. On this slide, on the top, it says the platform and how we got here. So, if you have a single database, you have a single application, and you have not so much users and not so much requests going to your application, you don't have a real-time problem. You store your data to a database, you query it, and you have everything in real time because it's everything there. But I know as we have lots of traffic, we needed to scale our systems so that we can reach big throughput. So a little bit of history. At the beginning, we had only one node processing all the traffic, and of course, one database. And it was all real time, it was no problem. But as traffic increased, we had to make things different, and we introduced several databases. Then we introduced multiple transaction databases and multiple monolith nodes. And we kind of did it, but everything needed to be, everything became a little slower. Of course, the querying of the data became complex. When you have multiple databases, you have to query and then merge the results. You have when you have aggregates, when you aggregate the reports and you have multiple databases, always some databases maybe go down. If you have more databases, it's more of a probability. Then you have missing data and you have false reports. So. To solve this problem, we tried to introduce aggregation databases that pull data from with ATL, extraction, transform and load to another database, and then we queried for reports those databases. Okay, but in the meantime, we also started decoupling our big monolithic node that was way too big to scale development. You know, it's always easier to have smaller applications when you have a big development team. And we were counting 150 developers. It would be hard to develop this application. No one would know what this application does. So we introduced like microservice applications, but some are bigger, some are smaller. But we have this platform of microservices. Okay, the traffic increased, and of course the non-transactional queries became a problem. What I mean by that? It's you have your traffic, and your nodes that are processing those traffic are working okay. They're storing data to databases, but you have several other applications making requests to those databases to read data, I don't know, some reports, of course, you have the aggregated databases. They're also pooling data, and they're slowing down our throughput to those nodes that should scale and should have a bigger throughput. So another approach was that our database team introduced a thing called Green. It's operational data store and data warehouse, which should aggregate all of Infobip data to those servers. It's not a single server. It's like a full scale of big, powerful machines. And with that, they achieved like near real-time information that could be read from those databases. And of course, we centralized the reporting, and we had exact numbers, and it was it was a thing that was working good. But of course, those databases overloaded of some of our core nodes and our core traffic databases. And okay, but they also provided specialized indexes and aggregations, so that fast reports that are queried oftenly can be get in fast time. But still, we have this problem of out of sync. So the queries to those databases were not slow. The query are still good, but the data is missing. That's the key. It's not the response time. It's the sync of data. So this sync, out of sync, it's from 1 minute to 60 minutes, but usually it's below 5 or 10 minutes. But you never know. It depends on the load of the system. So okay, another thing missing on this slide. It says our path towards real-time data. Okay, this green approach, this big data warehouse, things rather abstractly. You have tables in those databases, you have tables in those databases, you you pull the traffic from them, you replicate, and then you have data in that place from all our data centers and all tables. Of course, you can define it for ones that you need and something, but it consists of big hardware. And it's not so easy to scale. We have replication, but we can scale out to get much more throughput. And of course, they were doing things abstractly and specialized the aggregation indexes and views for those things that are for the particular use cases, but still they dependent on the syncing of data from those master databases to the data warehouse, and still not real time. And our approach was to use use case per use case basis. So we have this use case I presented you before, and we try to solve this problem. Not doing things like we should get this real time for all our data that we use. And because it's really not always needed, the real time stuff. Okay, and one other thing is the horizontal scalability. In this approach, we try to leverage the architecture used by big data giants that scaled their applications horizontally, so they, with traffic increase, can have also bigger throughput and so on. One of the things we got when we were researching was the Lambda architecture. Not to be confused, there's nothing to do with Lambdas in Java 8, presented by Branko before. It's a generic idea. It's not a tool. It's not a nothing. It's just an abstract idea. that you have 3 layers of your system, and the data between should be split when the data arrives to your system. The data as arrives, it should be split to the batch layer, to the speed layer, and then doing with some magic, you should provide like data that is needed in real time. You process it faster, you make add more hardware, scale horizontally, use some special tools like Apache Storm or Apache Spark. And with the batch layer, you have your data being processed in the background. It's like latency of 15 minutes, maybe half an hour, depends on the use case. But this is the general idea. I will not go in details. You will see the slide. So we were thinking about this architecture and our current architecture. What is? Can we do it this way? So. In this slide you see how we build something of that architecture but using our current system. So this is the this is our central applications, which are lots of microservices. Which are using transactional databases, and here is the green database, our data warehouse operational data store that I was talking before. So our apps are storing data to the transactional databases, and green is pulling them, and we have actual real and correct data in that layer. So we proclaimed that this should be our batch layer. We have our data that is actual, and it's true. It has no conflicts. It's all good. It's here in the green database. Okay, but the real-time layer we introduced, and the data from a core system should be pushed to this real-time layer. And we have this 2 points that we call ingest points. The verb ingestion, because all the data coming to our system is actually being rerouted here also to a real-time layer. And we have, of course, different ones, because for this use case, we needed 2 points, but with several maybe other use cases, you'll maybe have different points. Okay, the real-time layer processes the data and also storages this data for real-time. And we have a query layer. Instead of having clients joining the results and thinking about are the results real-time or batch or something, we use this query layer to have the knowledge of if the data is all merged and good. And of course the applications are approaching this query layer. That's about it. And when you and that's about it. This should be the real-time, the batch layer / serving layer and our query layer, but the layer doesn't exist as it in the Lambda architecture, but we thought it would be a good idea to have it like this. Okay. Let's go through the details of the real-time layer. For our particular use case, we had 2 microservices which are processing the data that we needed for aggregations and have it in real time. You said so the expenses and the counts. So the billing information about counts and expenses are in the billing service, which is we used for the billing ingest point. And another point is the IP core. That's our core node that processes all the traffic. And we send those data to our newly formed data ingestion service. That's a simple service like Spring Boot application. Of course, multiple nodes and something. I will explain maybe details later. So in this process, we only pair those messages from those two services to get the data that we want to aggregate. Because we don't have, on the IP core node, we have only the, let's say, if you send a campaign, you have an ID of this campaign. And this ID you have only on the core node, but the data of the traffic you have only on the billing node. So you have to somehow merge it together. And in this service, we merge these two messages together, compose a new one, and send this message further in processing. But it's no more processing. This is the message. It contains a single point of data, like count and count of a single message and the expense of this message. So we store this message to a Kafka cluster. Kafka, I will talk just a little later about it. And let's treat it like a queue. We store this message to a queue, and then we have a Druid cluster. Also, I will talk later about it. Process pulls those messages out of that queue and aggregates. This Druid cluster processes the data, aggregates them, and stores them in some kind of storage. Okay. This is something like of data that is flowing. This is one message. Okay. Just regular, we have some timestamp, we have a campaign ID, some currency data, our counts. Of course, it's a delta, notice this. It's a delta, it's not a fixed amount. That's particularly important for doing aggregations. Okay, this message is sent to a Kafka cluster, and that's there are a lot of details about the Druid cluster, but I don't have time to explain them all, so I will just explain the architecture in the whole. After that, we have the query layer I was talking before. It uses, it is approached by our other applications or web applications or internal or outside applications, and it knows where the data is. So we choose how to read and merge data here. This is the point. But we have two approaches. We are currently working on still how we will read the data. Because as the Druid cluster has all the data we process. That when we started, it aggregates all the data, and we have like it can be like for months. That's not a problem. But our true data is in the batch layer. So we kind of like we don't want to depend on this real-time nodes. We don't have still how this technology will work. How will we have managed to have a solution, but we don't want to depend on it. So we use like something like for an hour. We decide to read the data for an hour from the real time, and then merge the results with the green databases. Something like this is going on, but depending on your use case, we have some things that will not work this way. Okay. Here is the request that the data query service sends to the Druid cluster. It says like a regular, everybody knows SQL, it's a regular group by query, and you have dimensions and metrics that you aggregate on. So it's rather simple as a query protocol. It's querying the data. Do you see this? It's rather a small font, so sorry. And of course, the response from Druid is something like this. It's the aggregated dimension values and the metrics that are amounts of sums and expenses. Just be back on a slide before. One thing about Druid is it stores all data in a time-based fashion. So you can all data can be queried grouped by timestamp. So when you have this query that is you see the specifier granularity. It says how much do you want the data to be, like 15 minutes, an hour that you have aggregations on. So you can actually have graphs of that data being like your traffic going in a minute, in a 15-minute period, in an hour, in a days, and so on. But for this use case, we use it all, because we only need the sums. But we have some graphs for the next use case. Okay. Kafka. Just a few words. It's a typical, you can treat it as a queue, but it really isn't. It has something specific called the consumer group. So this can be used in two ways. Kafka can be used in two ways, as a queue or a publish subscribe. So depending on the use case, you can broadcast your messages being sent to the queue to all the consumers, or you can split. Sorry. Just a second. Okay. So depending on the use case, you can have applications pulling from that queue, processing parallel stuff, depending on how you define this consumer group. And of course, this Kafka is built by LinkedIn, so it can scale like clusters of more than hundreds of servers and store data like terabytes and terabytes. We, of course, don't need it, but we use this tool to provide higher availability and have things like flying fast with this use case. And here's a thing about Druid. It's actually Druid itself. It's composed of a Lambda architecture. It provides 2 layers, which can be. We don't use it this way. But you can have the real time and the batch layer inside Druid, and the real time because it's composed of multiple nodes that are real time nodes and like historical nodes, which should be something like batch layer. Those nodes for the real time are optimized to store data in memory and periodically store it. And the queries from them are much faster, and you can access it like in sub-seconds. Of course, depending on how you configure the cluster, there's a lot of things to. It's not so simple to drive in but of course we tried and we achieved this thing that it gets to a point where we could process. Like we could stop this Druid cluster, and the Kafka is getting filled with messages from our system. And we after that restarted this system, which is multiple. We shut down all the cluster, and then restarted it, and it processes all the messages, like 3,000 messages per second, and this is not optimized. But this just was like okay, this is the. With optimizations and better scaling of the system could be even achieved a lot more. So we actually use it to process data because it has something called the fire hose. A fire hose is is a concept in Druid that uses something like configurable plugin that can pull data from various data sources. One of those is Kafka. And it just, you define those, this firehose, you define the data, how the message that we received from Kafka is like a JSON, it has all those properties, you define the dimensions, you define the metrics, and it just pulls data and aggregates on the rules that you give to this, in this configuration. Okay. Okay, the title says numbers and conclusions. Conclusion. This is some numbers of data flowing from our system to the data ingestion service on the first line. You see the first line is ingest points towards data ingestion service. It's the sum of the billing ingest point and the IP core ingest point. Because for one message, we have to process 2 messages actually in our ingestion service. And we have like the sum of it, it's 770 messages per second. But this is only, we didn't do a real load testing. This is our production data that we tried to achieve. But we didn't have the possibility to have it more. That's about it. And of course, the data ingestion service, as pairs data, it pushes data towards Kafka, and we see here a little of speed down. This is the where our service we have like slowing down things. But this is also the key point to that this is usually in real big data environments like Facebook and so on. They use it, they don't use, of course, a small service that is written in Spring Boot and have like 2 nodes. It's Storm, something like called Storm or Apache Samza or something, a stream processor. So that you can scale for lots of throughput. But we actually don't need in this situation those right now. Also, we experimented with those, but for this use case and for several others, we will surely not need it anytime. But we will we will experiment further on. So, as I was saying before, the last row says the Druid firehose pull and aggregate from Kafka. This is the number when we shut down the cluster and try to get how much and how much speed it will process the data. Because what is this important? If you have some, we have, of course, two servers of Druid that are, but if your all 2 servers go down, you will still have messages in Kafka, and you can replay those messages and get in real time. And this is important because if you can you can use the numbers like it will achieve real time in a couple of minutes for this traffic. So, again, this is a use case. This application had rewritten and make it read data from our data query service, and this data is actually with less than 2 seconds delay in real time. What are the problems and the challenges? With this approach, we add complexity to the flow of our system, and we have, of course, the maintenance of our ingest points, because you have to, this is also code. When something changes in the system, maybe you have also changed that code. Of course, it's operational knowledge of Kafka and Druid. It's non-existent. Everybody uses it, but nobody knows really how to use it the real way. Okay, and of course we have scaling scaling problems with Droid, but there's being things done. If this goes to a good direction, and we have some other problems with Droid, but it should be really resolved. And that's about it.
Thank you, Davor. Due to shortage of time, all Q&A in the coffee break.
Yeah, yes. If you have any questions, please, it's no problem.